I hope the screen is visible to all of you. So the course that we are going to study this semester is called Chemical Reaction Engineering Part 2. And the course code is CHE-S402. And we'll start off the semester trying to learn the subject in the online mode till we are allowed to come back to classroom teaching. And I'm Dr. Brishti Mitra, and I will be your course instructor for this one, for this course. And this is my email ID. You can contact me over Google Classroom or through my email whenever you want to for any questions regarding the course. And if you need to contact me through WhatsApp, please do it during office hours. So as with the previous courses, this lecture material for this course is meant only for the students who are registered for CHE-S 402 in this semester, and the material should not be shared or distributed or printed without my consent. Okay, so now let us look at any chemical process and try to understand what are the steps which are involved in that. And as a chemical engineer, since you're in the 4th year, I'm sure all of you are aware that the primary job of a chemical engineer is to design, develop, and finally operate an industrial process whereby we can convert the raw materials into commercially useful products. And in this process where we carry out the conversion, that means in any industrial process, there could be several steps, and which we differentiate as the pre-reaction step, the reaction step, and the post-reaction step. The one which is in the center, which is we are according to this figure, which is known as stage 3, is where the actual reaction is taking place, where your raw materials are getting converted into products. But that is not the only unit in an industrial process, unlike what would be there in a chemical lab or a chemistry lab. So here we have several units which are present before the reaction step, and there are several which is after the reaction step. For example, before the reaction step, we might have several units whereby we prepare the reactants so that now they can be now introduced into the reactor. Sorry. What do you mean by prepare? Preparing means we might carry out processes such as heating, such as vaporizing the feed, such as breaking up the sizes of the solid raw materials. So these are preparation methods, and which are a part of the pre-reaction section. And in the post-reaction section, what we have is that once the reaction happens, the products which come out are often mixed with unreacted reactants in case our conversion is not 100%. And we might have some side reactions where we have some byproducts, or there could be some waste products, desirable materials, which is also formed. Now, these have to be removed from the primary product. Otherwise, we will not be able to sell the product in the market. So the separation steps which are involved beyond the reaction steps and separation and purification steps, all of these together form the post-reaction set of the components which are there. So, but however, if you see that these two portions which are marked out in blue, that is the pre-reaction and the post-reaction sections, most of these are physical operations. That means we have separation units, we have size reduction units, we have mixing units, but they all involve physical processes, such as mixing, vaporization, distillation, absorption, extraction. Any of these could be there. And the center one, or the middle one, which is known as the heart of your industrial plant, is the reactor where the actual chemical reaction takes place. Now, this chemical reaction, which we are using to form our product, it could be a single reaction or it could be multiple reactions. If you want to understand what do I mean by that, suppose when we are trying to make ammonia in a reactor, the feed that is introduced is nitrogen and hydrogen, and 1 mole of nitrogen reacts with 1 mole of hydrogen to form 2 moles of ammonia via one single reaction. However, when you go ahead and try to form urea, there are 2 steps to this process. First, the ammonia and carbon dioxide react to form carbamate, and then the carbamate breaks down to form water and urea. So this is a multiple reaction or a 2-step reaction. So in an industrial process, we could have either a single or a multiple one. And the materials may be present in a single phase or in a multiple phase. So what do you mean by that? Say, for example, if my reactants are gases and my products are also gases, and we are not using any catalyst or solid or liquid catalyst out there, then this could be a single phase reaction. Or if you have a gaseous reactant and the products are also gases, but we are using a solid catalyst, then it becomes a multi-phase reaction because we are talking about a solid as well as a gas. These are the two different phases that we are talking about. And these reactions may actually take place in different kinds of reactors. You have studied a bit about reactors before this, and whereby you have learned that the reactors such as a plug flow reactor, there could be a CSTR, there could be a packed bed reactor, there could be a slurry reactor. So these are the various kinds of reactors where we might have these reactions happening. Now, in our syllabus, what happens is that we have two courses on reaction engineering. The first one is called Chemical Reaction Engineering 1, that is CHE-S304. And the second one is called Chemical Reaction Engineering 2, CHE-S402, which we are going to study now. Now, in the Chemical Reaction Engineering 1, which you studied in your sixth semester or fifth semester, I don't remember exactly, you have covered all the basic aspects of reaction engineering. That means what do you mean by kinetics? What is the order? What is the molecularity of a reaction? How to carry out experiments in the lab and then find out the rate of a reaction using either the differential method or we are using the integral method. That means whether a reaction is a first order reaction, reaction is a second order reaction, or a fractional order reaction, whichever one it might be. Now, then we go on and you had learned how to do the designing of ideal reactors. So when we talk about ideal reactors, what are we talking about? Say reactors such as a batch reactor or a plug flow reactor or a continuously stirred tank reactor. But the behavior of these reactors are ideal. That means what? Suppose we are talking about a plug flow reactor, you know that the concentration of the reactants change when we go from the inlet of the reactor to the outlet of the reactor. That means there's a change in concentration in the axial direction. However, the concentration in the radial direction remains constant at every point. So if a reactor works like an ideal or a perfect plug flow reactor, this would be true for at whatever is the condition, whatever point of the reactor that we are talking about. Or, for example, if you're talking about a continuously stirred tank reactor, then as is known for an ideal reactor, that the concentration of the material inside will be the same at any point inside the reactor. So now these are all about the different types of reactors which are there, and you learned how to do the design. That means you learned how to find out the volume if you know what reaction is carried out, what is the conversion that is required, and you found out based on different kinetics. And also we have learned that suppose instead of a single reaction, we have a series reaction or a parallel reaction. All of that was covered in your Reaction Engineering 1 course. Then we came about talking about heat effects and pressure effects. Heat effects means essentially that if a reaction is exothermic or endothermic, that means either the heat is given out or the heat is absorbed. In that particular case, how do we incorporate that into the reactor design? How does it influence our reactor design? That means we're talking about energy balances along with our mass balance. And finally, you might have studied about non-ideal reactors, that when reactors due to a non-ideal flow do not behave either as an ideal plug flow reactor or an ideal CSTR, how does that non-ideality of flow affect your conversion? Now, so in any reactor design course, the ultimate goal of the course is to learn how to design a reactor. So when we want to do that, what are the inputs that are required? Some of the inputs that are required, let me get my pointer out here. So some of the inputs that are required are reaction kinetics. That means what is the rate expression or what is the order of my reaction, which we are going to use to find out the volume of my reactor. So the rate expression is important. Then we need to know whether my reactor is happening under adiabatic conditions or isothermal conditions, whether it's an exothermic reaction, whether it's an endothermic reaction. So how does addition or removal of heat affect the reactor design? The third thing is the pressure effect. So by pressure effect, what I mean is that how does changing the pressure affect the design of my reactor. This is primarily important when we are talking about gas phase reactions, because in the case of gas phase, the concentration and the pressure are related to each other. Gases are compressible. So once you change the pressure, the concentrate, it will have an effect on the concentration. The partial pressure will get affected and my concentration gets affected. And if concentration gets affected, since my rate expression, say for example, on a first order reaction, it will be minus RA is equal to K into CA. If CA gets affected, that definitely will have an effect on my reactor design. However, in the case of liquid phase reactions, these pressure effects are not very important because liquids are mostly or usually incompressible, as we call it. Apart from that, we have the non-ideal. So once we have done all from here we'll get the mass balance, then we have the energy balance, then we have the momentum balance, and then we'll talk about non-ideal flow patterns. How all of these together can be put together to find out how they influence my reactor design, and finally find out how to find out the volume of a reactor or design an entire reactor that we have to do. Now, in your Reaction Engineering 1 course, you have done all of these, but everything was done for homogeneous systems. That means when the material was present in one single phase, either maybe it's a gas phase or it could be a liquid phase reaction, but there was only one single phase involved, and hence we call them the homogeneous systems. In our course this semester, what we are going to do is that we are going to learn about heterogeneous systems. In the case of heterogeneous systems, what happens is that, in the heterogeneous systems, there are more than one phase that is involved out here. That means there could be a gas-solid reaction, it could be a solid-liquid reaction, it could be a gas-liquid reaction, all of these which involve more than, or it could be a gas-liquid-solid reaction. Any of these reactions which involve more than one phase, they are known as heterogeneous. So heterogeneous reactions which have multiple phases involving multiple phases, they could be either a catalytic reaction or they could be a non-catalytic reaction. Not everything. So heterogeneous reactions can be either catalytic or it can be non-catalytic. So let us look at some examples. So for example, if you're talking about a catalytic reaction, the example that we could take is the conversion of cyclohexane to benzene. Cyclohexane, when the reaction is carried out, is in the gas phase. And the catalyst which we are using for this conversion is a platinum alumina catalyst, which is in the solid phase. The product which is formed is benzene and hydrogen. Both of these are in the gas phase. So here the two phases involved are gas and solid. One is the catalyst, and this is the gas is the reactants, and the products both are in the gas phase. So this is a catalytic heterogeneous reaction. Can we have a catalytic homogeneous reaction? Yes, we can. In a case of a catalytic homogeneous reaction, the reactants, the products, the catalyst, all must be there in a single phase. This is often seen when we talk about liquid phase reactions. If I have a catalyst which is a liquid, then the reactants and products, if they are also liquids, then it becomes a homogeneous reaction, but it could be a catalytic homogeneous reaction. Now, if I look at what kind of a reaction is a non-catalytic heterogeneous reaction, the example that I could take is when we oxidize zinc sulfide. Zinc sulfide is a solid. You react it with oxygen, which is in the gas phase, and my product is zinc oxide, which is a solid, and sulfur dioxide, which is a gas. So there are two phases involved, both in the reactants and products. Solid gas in the reactants and solid and gas in the products. And for example, if you are talking about calcium carbonate solid, then calcium carbonate can dissociate into calcium oxide solid and carbon dioxide gas. So calcium oxide is a solid one and carbon dioxide is the gas. So there are two phases which are involved, and that is what makes it a heterogeneous reaction. But these reactions do not involve any catalysts. So and there's one more thing that we must observe out here, that unlike a steady state operation involving a gas solid catalytic reaction like the one we had seen earlier, these non-catalytic gas solid reactions are intrinsically dynamic. That means they are non-steady state. So why do I say that? Let's have a look. Say, for example, calcium carbonate is a solid. It's a solid lump, and your heating it so that it dissociates into calcium oxide and carbon dioxide. Once this dissociation happens, you will see there's a decrease in the weight of the calcium carbonate, and the size also becomes smaller. So there is a change in the size of the material, what we start off with the reactants and what we get in the product, because part of it is being converted to a gas. So since there's a change in the nature with time, these reactions are essentially dynamic or non-steady state in nature. This does not happen in the case of a catalytic gas-solid reaction, where the catalyst, which is in the solid phase, there is no change in the catalyst before and after the reaction, nothing changes. That is what the characteristics of a catalyst is. Now, what happens? What is so special about heterogeneous systems that we have to devote an entire course on that? So when we have a heterogeneous system, there are two complicating factors that come in. One is called the complication of the rate expression, and the other one is the complication of the contacting pattern of the multiphase system. Now, what do I mean by that? That in the case of homogeneous systems also, the rate expression was important. Otherwise, we could not have done any reactor design. That means we need to know how does the reactant behave with what is how is the concentration dependence of in terms of the reaction rate. Apart from that, when we're talking about multiple phases, then the contacting patterns of these phases become important. Just like if you think about it, that if you have an absorber, unless there's a very good interfacial area and a contact between the gas and the liquid, the mass transfer will not take place. And unless mass transfer takes place, your absorption process will not happen. The same thing what happens is when we have a multiphase reaction, the mass transfer from one phase to another becomes an important one. And that mass transfer essentially depends on the contacting pattern. How well they are contacted, what is the mode of contacting, and that will determine the mass transfer, which in turn will also influence my rate expression. So the phase boundaries, which are inherent in heterogeneous systems, require that the transport processes, that means mass and heat transfer, as well as the intrinsic reaction rate must be accounted for in reactor design. So this, because it was a single phase in the case of homogeneous reactions, this problem of mass transfer was not there. And that is why when you study this course, by the time you have finished your mass transfer courses, so you know your principles of mass transfer, what does it depend on, etc. You're already aware of these parts or these factors which are there. So when we try to design a reactor for a heterogeneous system, there are two things that are important. One is the mass transfer and one is the reaction rate. So if you look at the components which influence a reactor design, apart from the factors which were already there for homogeneous reactions, that means the reaction rate, then the heat transfer effects, then the pressure effects, then the non-ideal flow patterns which are there, all of these were important in homogeneous cases, and it will be equally important in the case of a design of a heterogeneous reaction. But over and above, we have another factor that comes into place, which is called the mass transfer effects. And very soon you will see that how this mass transfer actually either slows down or in most of the cases slows down the rate of a reaction. There's another thing I want you to note out here is that when we are talking about reaction rates, I have used a term which is called intrinsic reaction rate. So what is intrinsic reaction rate? Intrinsic reaction rate means a reaction rate which is not influenced by mass transfer. This is the real reaction rate where no influence of mass transfer is felt out here. So mass transfer and intrinsic reaction rate together will lead to something else, which we will learn right now after this. So here, like I had mentioned, again, I'm repeating it, that for a design of a heterogeneous reactor, apart from reaction kinetics, heat transfer effects, pressure effects, non-ideal flow patterns, we also have another very important factor, which is the effect of mass transfer. Now let us understand this, try to understand this effect of mass transfer as is there. For a gas-solid reaction, the different steps which are involved are the movement of the gaseous reactant from the bulk to the solid surface through the gas film, reaction at the solid surface, and the reverse movement of the gaseous product from the solid to the bulk gas through the gas film. Now, let me see. try to understand this by means of an example. See, whenever we talk about heterogeneous system, there'll be two terms that I will talk about very often. One is called the bulk, and the other one is called the surface. So there's a concentration of the reactants in the bulk, and there'll be a concentration of the reactant at the surface. The bulk concentration, say for example, is known as Cb, and the surface concentration is known as Cs. That is, so let us see what is the difference between the two. Now, here is my solid reactant, and around the reactant, I have a film of gas, which is known as the gas film. Now, the gas concentration from the bulk, for example, let me get my pen out here. It comes like this. It's a straight concentration from the bulk. And then there's a drop in the concentration due to mass transfer. This drop in concentration due to mass transfer is because of the fact that there is a mass transfer effect causes a change in the concentration from the bulk to the surface. That means there is a, due to the effect of mass transfer, there's a drop in the concentration. And this drop in concentration changes the surface is a different value from the bulk. And usually the value in the bulk is greater than the concentration at the surface. So the bulk, however, if you notice that we usually cannot measure the concentration on the surface. What can be measured is the bulk concentration. Why there's that? Because bulk is where I'm sending in my reactant. So I know exactly what my concentration is. I can measure it. However, I cannot measure the surface concentration. I can only do that if I have a particular probe right on the surface of my solid, and then you can have a reaction that is, and you can find out what is the concentration out here. So since that is very difficult to achieve, what I know is my bulk, but that is not the real concentration. The concentration of the surface is known as CS, or the surface concentration. So let us look at this example and see what happens. The example says that this is a piece of carbon which gets oxidized in the air, or we are getting oxidizing it with oxygen. So in the bulk, we have the concentration of oxygen, and then this oxygen travels from the bulk through the gas film and reaches the surface of the carbon. And when it reaches the surface of the carbon, the concentration is Cs, and the bulk concentration is Cb, with Cb being greater than Cs. Now, when this drop happens, where is the reaction happening? The reaction is happening at this concentration. Now think about it, that my reaction is happening at the surface concentration. What is the rate? The rate is, say if it's a first order reaction, then it's K into CAS, the real constant, the rate which should be. But we cannot measure CAS. What we can measure is CB. So what happens is that if I try to write out the rate in terms of CB, I will get an incorrect value from what it really is, because in reality the concentration is actually lower than CB, and because the concentration is CS, and the rate is lower than what it should be had the reaction happened at the concentration of the bulk. This is because of mass transfer. So you see that there's mass transfer of oxygen from the bulk to the surface. Then there's a reaction at the surface. And once the reaction happens, the product CO2 is formed. This CO2 now has to diffuse back from the surface to the bulk. So there are three steps which are involved. The resistance of mass transfer in the gas film results in the concentration of the solid surface being lower than that of the bulk concentration. So this is for a lower concentration. And as the surface concentration is difficult to determine, the rate that is determined, which is in terms of the bulk concentration, this rate is known as the global rate. So this is another term. Last time we talked about intrinsic rate, and now we are talking about a global rate. So global rate is something which also includes the effect of mass transfer. So this, if you realize that this example that I had taken is an example for a gas-solid non-catalytic reaction. Now let us look at, suppose we say that we are actually having a catalytic reaction on the surface of a non-porous catalyst. Say this is my catalyst, spherical catalyst pellet. It is non-porous in nature. That means nothing is going inside the pellet. All the reaction is happening on the surface of the catalyst, which is there, and hence we call it a non-porous catalyst. This is a gas phase reaction. The reactant is A and the product is B. So the gas phase comes into the surface of the solid. This is a catalyst. It undergoes a catalytic reaction and leads to the formation of B. So the first thing that we have is that we have a bulk concentration of A, which is known as Cb, and when it reaches the surface, it becomes the surface concentration, that is Cs. These are all concentrations of A going to B. Concentrations of the reactant A. Now, the rate of transport of A, the reactant A, from the bulk to the surface is solid catalyst surface can be given as Rp is equal to Km into Cb minus Cs. So what is Km? Km is my mass transfer coefficient. Depending on the unit, it could either you can have something what is written I've written out here as Km, or it sometimes can be written in terms of kg, which is something you might have seen in your mass transfer books. It all depends on the unit. For example, Km, what is K? Km, mass transfer coefficient, in Am is the external area per unit mass of the catalyst. The units are important out here. And this is the rate of mass transfer. And the difference in concentrations is Cb minus Cs. Because of this concentration gradient, the material moves from the surface, from the bulk to the surface. And once it reaches the surface, there's a reaction. And the rate of the reaction is given by Rr is equal to K into Cs. Now, at steady state, the rate of mass transfer is equal to the rate of the reaction. So, Km Am Cb minus Cs is equal to K into Cs. So, this happens at steady state. And as Cs is less than Cb or Cb is less than Cs, you can see that the mass transfer resistance actually reduces the rate of reaction. Now, if I open up this bracket, what do I get? Km Am into Cb minus Km Am into Cs is equal to K into Cs. Now, if I try to find out the non-measurable part from here, that means try to find out what we cannot measure, the concentration at the surface, this is Cs is equal to Km Am divided by Km Am plus K. This into Cb. And if I put this expression of Cs in the rate expression for in order to find out this, then what I get that the reaction rate R is equal to Km Am into K divided by Km Am plus K into Cb. This reaction rate is known as the global rate, or it is called the overall rate, it is called the observed rate, or is called the measured rate. All of these mean the same thing. So if I carry out a heterogeneous reaction in my laboratory and I measure the measured rate, it will be called the global rate because it will have the effect of both kinetics as well as mass transfer. Where do you see that? See, 1 by K gives you the effect of the kinetics and 1 by Km Am gives you the effect of mass transfer. Now, if I look at this system out here, which is called the gas solid system, what do I have? I have, this is my surface concentration, Cs out here, and this is my bulk concentration, Cb. And I said that the bulk concentration is higher. So slowly the concentration drops, and this distance is the film, essentially the gas film, where the concentration changes from Cb to Cs. Now, if you consider a system where there is no influence of mass transfer, that means the rate of mass transfer is very fast. When is that possible? When the value of Km Am is very large, then the mass transfer is going to be a very fast step. So when the mass transfer is a very fast step, there's hardly any difference in concentration between the bulk and the surface. So Cb is almost equal to Cs. So this, instead of having a drop, we will have a straight line. And the moment it comes out here, there will be a reaction. So here what is happening is that the mass transfer is a very fast step. Comparatively, reaction is slower. So mass transfer being a very fast step, that means my Km Am value is large. Now, if we look at the rate expression, if my Km Am value is large, then 1 by Km Am is small. So 1 by Km Am, if it's small, we can ignore it. And the rate that comes out is only equal to K into Cb. So in this case, my rate is equal to K into Cb. That means the rate is entirely governed by the reaction. And that is why this is, in this case, it is called the reaction controlled rate. Next comes the situation where we have a diffusion control. What do I mean by that? In this case, the rate of mass transfer is very slow, and the reaction kinetics, that is, the rate of reaction is very fast. So the rate of mass transfer is so slow that that is the one that becomes a deciding factor. The moment it reaches the surface of the catalyst, it immediately undergoes a reaction and the constant complete conversion, and the concentration of the reactant becomes equal to zero. So here, this dotted line is the one in that particular case. So here what happens, that the rate of reaction is very, very fast, and the rate of mass transfer is very small. So if the rate of reaction is very fast, that means K is very large, then 1 by K is small and we can ignore it. And in this case, now what happens, my rate becomes equal to, it becomes just dependent on mass transfer. That is Km, Am, Am, Am into Cb. That means it is entirely controlled by mass transfer. That is why it is known as diffusion control. That means mass transfer is the one that is going to control the reaction. Now, it is highly possible that in most situations, you will never find either a completely diffusion controlled one or a completely reaction controlled one. And what we have is essentially somewhere in between, where the reaction is also playing a part and the mass transfer is also important. So the actual global rate has got the influence of both reaction rate as well as mass transfer. And you can see that the rate of my reaction is equal to Cb, and in the denominator what we have is that we have the summation of the resistances. Let me go back to my pointer. Okay, so we have a sum of the resistances out here. Now, if you look at other multi-phase systems, what do we see? That here we have a gas-liquid system, which is like a bubble reactor. And here we have a gas-liquid-solid system, which is the slurry reactor. Now, if I try to understand how does mass transfer affect the situations or the design in the case of a bubble reactor or a slurry reactor, then we can look at each of these pictures or the concentration profiles out here. So in a bubble reactor, what do we have? We have the gas going out in the form of bubbles through a continuous phase of liquid. So in a bubble reactor, the gas is in a discrete phase and the liquid is in the continuous phase. This becomes very important to understand what is a continuous phase and what is a discrete phase. The one it is present in smaller units, that is known as a continuous phase, a discrete phase, and the one that is continuously present, this is called the continuous phase. That means the liquid is my continuous phase. So if you look at the concentration gradients out here, what do I have out here? Inside the gas bubble, we have the concentration is given by CAG. At the surface, the concentration is CAGI. So what happens inside the gas bubble, the concentration is constant. So we have a straight line. And when it comes to the surface, and around the surface, there's a gas film. And because of mass transfer, there's a drop in concentration. So the CAG changes from CAG to CAGI. I stands for the interface. And what is the interface? This is the interface between the gas and the liquid, the gas film and the liquid film. If you remember your two-film theory, in your mass transfer, you will remember that there are resistances both in the gas film side and the liquid film side. And the concentrations at the interface are related by the Henry's law. So at the surface, the concentration of the liquid at the interface is known as CALI. And as it travels through the liquid film, there's a drop in concentration. And then there's a constant concentration in the liquid area that is equal to CAL. So here, there are two drops that we observe. One is in the gas film and the other one is in the liquid film. Now, the other condition where we have the slurry reactor, what happens in the slurry reactor is that we have now three phases. One is the liquid continuous phase, we have the gas discrete phase, and then we have solid catalysts where the reaction is taking place. Now, if I look at the mass transfer possibilities in such a situation, let us see what happens. We have the gas bubble. where the concentration is constant. And then there's a drop in concentration in the gas film, and the concentration changes from CAG to CAGI at the interface. And this concentration, gas concentration, is now related to the liquid concentration by Henry's law. And the concentration in the liquid phase is known as CALI, I again standing for interface. And through the liquid film, there's a drop in concentration, and the concentration comes down to CAL. Once we reach the bulk liquid, then the concentration remains constant till it goes to the film, liquid film surrounding the catalyst. Now, this liquid film surrounding the catalyst, because it is a film, again, there'll be a drop in concentration due to mass transfer resistance, and the concentration changes from CAL to CAS, S standing for the surface. This solid catalyst, however, is not non-porous. It's a porous catalyst, so material can go inside the catalyst pores. I'll describe this more later about porous catalysts. And because it can go inside the catalyst pore, there's again a drop in concentration, and the drop in concentration is a function of distance. So this drop is known as CAS, and from CAS to CA, and CA changes along the length, along the radius. So here there are several other mass transfer resistances which are involved, apart from the gas film, the liquid film out here, then there's a liquid film out here, and there's a concentration gradient inside my catalyst. So all of these mass transfer resistances are going to influence the rate of your reaction, which will ultimately have an effect on your reactor design. So I think I'm going to stop out here today, and we'll continue from here in the next class. So I'm going to stop sharing, and we will continue from here in the next class.